In this video, we're going to examine solutions from a perspective that's a little different from the rest of this unit. It turns out that when you compare two liquid samples, a pure substance and one that has something dissolved in it, the solution has several physical properties that change just by virtue of the fact that it's a solution. It doesn't matter what the dissolved stuff is, only how much of it is present. These are called colligative properties, and we're going to introduce a few of them here. First up, we've got a phenomenon known as vapor pressure lowering. Just as a reminder, the vapor pressure of a liquid is the average pressure exerted by the particles of that liquid that manage to escape into the gas phase at a given temperature. Every type of material has a vapor pressure, but it turns out that the vapor pressure of a pure substance changes, in a predictable way, when you dissolve something non-volatile into it. What we find is that the solvent's vapor pressure is lowered, which means that the solvent's molecules are spending less time on average up in the gas phase. It's tempting to explain this phenomenon in a couple of different ways. You might think at first that since vapor pressure depends on the strengths of the intermolecular forces that hold the condensed liquid phase together, the addition of solute particles must be leading to stronger IMFs in the solution. That's compelling reasoning, and it might be true for certain solutes like the ones pictured here. But remember that colligative properties actually don't depend on the kind of solute we're using. We see the exact same effect from a solute that only provides opportunities for weaker interactions with solvent molecules. A more common explanation given in many textbooks has to do with crowding at the surface. Solvent molecules have to be at the surface of the liquid in order to escape into the gas phase, and if there's something else taking up space at that interface, there's less opportunity for those volatile molecules to escape. In truth, there's a little more going on here than meets the eye. We'd need some energy-related concepts from further down the road to fully explain why a mixture like this favors staying together as a solution more than the pure solvent favors its liquid phase. You can stick a pin in that for now if you like, but the key point here is that this phenomenon only depends on the amount of dissolved solute. In fact, there's a simple relationship called Raoult's law that shows how vapor pressure is predicted to change as a solution gets more and more concentrated. Adding more solute will decrease the solvent's mole fraction here, so hopefully we can see that the vapor pressure will get lower and lower with more solute, according to this equation. Before going on, there is one more thing about this equation that will carry over to the rest of this video. When you're calculating the mole fraction here, you always need to take dissociation of your solute into account. Colligative properties depend on the amount of dissolved particles, so it really does matter for this calculation that your single mole of magnesium chloride, in this example, actually breaks up into 3 total moles of ions when it dissolves. There's a number called the Van Hoff factor that describes this multiplicity. Don't be surprised, by the way, if the numbers provided by a reference table for Van Hoff factors aren't exactly whole numbers. These factors are determined empirically, so they won't always line up exactly with what we expect for ionic compounds, for instance. When you're calculating the mole fraction of Raoult's law, though, you can simply multiply the moles of added solute by the Van Hoff factor to get the total average amount of dissolved particles. The second colligative property we'll see here is directly related to the one we just covered. The boiling point of a substance is directly related to its vapor pressure, and all the same considerations are at play. If the vapor pressure of a certain solution is lower than the vapor pressure of the solvent alone, then it stands to reason that if you want to get all the solvent into the gas phase, it's going to take more energy to accomplish this for the solution. To put it plainly, the boiling point of the solution will be higher than the boiling point of the pure solvent. Just like the vapor pressure property, there's a formula that relates the difference in boiling points to the amount of dissolved material. A few things to watch for here, though. First, we're measuring the concentration in molality this time, which is different from before. Second, we have this boiling point elevation constant, which is an empirically determined value that you would look up for the particular solvent in question. And finally, it's important to remember that this formula doesn't actually give you the boiling point of the solution. It only gives you the change in boiling point that you'd expect to see for your concentration of solute. To solve problems around boiling point elevation, you often need to reference the original boiling point and then add on the quantity that you get from this formula. Moving on to our third colligative property, we have freezing point depression. It turns out that the unusual favorability of the solution state that we've been seeing so far doesn't just affect the liquid-gas phase transition. Leaving the liquid phase through freezing is also more difficult for a liquid once something is mixed into it. Here again, the physical explanation is a little complex, but suffice it for now to say that liquids can't freeze like they normally would, unless they exclude the solute particles from the ordered solid lattice that they're forming. There's an energy cost associated with separating out all that solute, and that's ultimately going to mean that you have to lower the temperature even more than usual in order to freeze your solution, compared to the pure solvent. Incidentally, this is why we put salt on the roads and sidewalks in winter. After the salt dissolves in the melted snow on these surfaces, they won't ice up again until the temperature gets low enough to overcome the freezing point depression effect. We have another formula to calculate this effect relative to the pure solvent, and you'll note that it looks just like the boiling point elevation formula, with only a different constant to distinguish them. Just remember that we have to subtract the value that this formula gives us from the freezing point of the pure solvent, whereas we added it when dealing with boiling points. Before moving on to the last property, it's worth noting how boiling point elevation and freezing point depression affect the phase diagram of a solvent. When we compare the diagram for a pure solvent to the diagram for a solution, we can see both effects at once, and the result is that the liquid phase just expands to take up a larger portion of the map. This shows again in a comprehensive visual way that the liquid state becomes more favorable overall when it exists as a mixture. One last property to discuss before we finish up, and this one needs a more complicated setup to see. Take those two liquid samples from the previous parts, and suppose we put them in separate chambers with a divider in between. If we open that divider so that the two samples can mix, we might expect something pretty mundane to happen. The pure solvent will mix with the solution, and after a certain amount of time we end up with a homogeneous mixture. That's exactly what will happen in the described setup. But now suppose that we have a membrane between the chambers that only lets solvent molecules through, and keeps the solute particles trapped on their side. In this case, we see something quite different. It's a phenomenon called osmosis, where there's a bulk movement of solvent from the pure side toward the solution side. Again, this process isn't affected by the type of solute that we have in the second chamber, so osmosis doesn't occur solely on the basis of the solute particles attracting the solvent with stronger intermolecular forces or anything like that. If we zoom in on the interface between the chambers, we see that the concentration of the solvent molecules on the left side looks like it's going to be higher than the concentration of the solvent molecules on the right side. Solvent on either side can freely cross the membrane, but since there are more solvent molecules per unit volume on the pure side, there are more chances for molecules on that side to cross over, and it stands to reason that there's going to be an overall mass movement over to the right. We'd say in this case that water is moving down its concentration gradient. This simple picture is still a little incomplete, just as it was with our vapor pressure discussion. We're leaving out some of the thermodynamics that describe additional reasons why the solution state is more favorable overall. But it's a decent way to start visualizing osmosis on the molecular level. One key thing to point out is that osmosis will theoretically continue until the solute concentration on both sides is equal, provided something else doesn't stop it. In our example with totally pure solvent on the left, this would actually never happen. So in the absence of outside forces, our final picture would eventually look like this, with the left chamber completely empty. The thing is, there almost always is some outside force resisting osmosis. In our example here, it would be the weight of the solution combined with the atmospheric pressure pushing back against the continued flow of solvent molecules. And in the case of a closed membrane, like a dialysis bag, it would be the pressure exerted by the membrane walls. This is actually the indirect way that we measure osmosis. Osmotic pressure is the pressure required to stop osmosis, and its formula is a function of solute concentration, as expected for colligative properties, and also temperature, which affects the rate of diffusion. We've had a long conceptual discussion in this video, and in the process we've introduced 4 colligative properties. The relevant formulas are shown here again for reference, and hopefully you now have a basis for understanding where they come from. Thanks for watching.